Okay, so thank you, Omar, for the presentation. Hello, everybody. I'm Javier Ruiz. I'm going to present you the work we've been doing within the Fascinate project about the gesture interaction with this so-called layer scene representation or format agnostic representation that the Fascinate project is working on. Basically, my talk is going to be a little bit about, I will tell you about the challenges that this representation has basically on the rendering part and on the interaction with the user. And then I will present you the solution that we have created about interacting with the content using human gestures. So I will tell you about the evolution that that these systems form from natural or remote control systems, usual ways of interaction with your TV. So I will tell you the functionalities of the system, and I will talk to you a little bit about the technical components. So I will tell you which building blocks you need or we have used to build a solution like this, okay? So what is this layer scene representation? You have heard it before. Some of my colleagues talked about it, but basically it's composed of a panorama image, so a very high resolution, 180 degrees image of the content. So you add some satellite cameras with it, so you know the relationship between the panorama image and the satellite cameras, but also you have some what we call region of interest. So these are regions of the panorama image, like this, that either a technician has selected, so something important is happening there, or some automatic systems that the scripting engine that you have seen in the demo before has selected as important within the panorama. So you have all this representation, all this information sent to the renderer. And then, of course, that brings some new challenges. For instance, in the rendering part, when you want to show that panorama within a flat screen, of course, the panorama is 180 degrees. It's not flat. It's spherical. So you have to render that into a flat screen. So, of course, you need to process and to do something about that. Also, you need to support multiple devices. So you have this extremely large panorama. You want to show it in a TV, high-resolution TV. You want to show it in a tablet. You want to show it in your phone. So you need to deal with that. Taking into account the interaction, of course, having these new representations allow you to do more things. So, for instance, you can navigate through the panorama, what we call, you can pan, tilt, and zoom, okay? So you have to allow the user to do that things. You can select regions of interest, so you want to go from the panorama to some regions, to some satellite cameras, go back to the panorama. So that's new interactions that you can do. Of course, this is not easily done with existing devices, so you can do that with your remote, but it's kind of, it gets complicated. You can do that with some other things. But the idea that we had is that, okay, let's explore new ways to do it. So let's explore new, what we call human-computer interfaces. And let's try to do that in a deviceless manner. So no remote control, no tablet, nor anything, just your hands. And we used a vision-based solution. So that's just a sensor that are seeing you. So we will communicate through gestures, okay? And when we talk about gestures, as I said, if you want to do this kind of interaction with remote controls, they get complicated easily, or you end up with many remotes. You have one for to changing channels, one to do the panning, the zooming, so that's a solution. It's not comfortable enough. Another solution is to use second screens. Of course, this is a very nice solution. I mean, now we are very used to have the phone in our hands. So you can use your phone, you can use your tablet to, for instance, navigate through a panorama on your TV, okay? Of course, some of the colleagues are using tablets to do that. That's a very nice solution, as I said. The only problem that it has is that, of course, it's a device. I mean, you need to have your tablet with you. I mean, if it's out of battery, you need to charge it, then you have to go to charge it. And, of course, a solution with nothing will be better. Something similar to what we're doing is this gesture is like these Wii remote things. Maybe you have heard about them, this Nintendo console that has this device, small like this, and then have some accelerometers in it, so it measures how it moves. So then you can do some gestures with the device, and they get transmitted to the screen. So you can navigate just by pointing, and it's a nice solution. Again, it's a device, so you have to take it with you. It can fall down, so you need to strap it to your hand, because then it can fall out and break your screen, things like that. Okay. Another solution, completely different, but I wanted to talk to it, is using your voice, of course. I mean, there are solutions like this Siri thing that iPhones have, that you can talk to your phone and it reacts. Of course, we can do that as well. But thinking about using these voice commands with a TV, it has mainly two problems, I would say. One of them is written here, is that it uses the same medium as the TV. So the TV is outputting sound, and you want to talk to it, so it can get a little bit confusing at the time. And also sometimes for some of the things that we want to do, like navigation, maybe it's a bit difficult to speak the command. So you can do top, top, left, left, and down, down, zoom in, zoom out. So it might not be much easier. So the solution that we propose is using what is called natural interfaces. So think about gestures that most of us do to symbol or to mean some things that the TV might understand. So we've got an example here, which is of this, which is the symbol that some of us do when we want our babies to get quiet. You know, we do like this. And it's more or less known that these gestures, we want the volume to go down. So maybe an interesting thing we'll do to associate this gesture with turning the volume down on your TV. So your TV will understand that when you do like this, it wants the volume to go down. Or similarly, you know, when you do this, it's like, I'm not hearing enough, please turn the volume up, okay? So that's the things we would like to explore, to interact. And a good thing about this is also that, as I said, it's deviceless. So you don't need anything with you, just stand up, do like this, and it works. So you don't need to grab your remote control, your tablet, or your phone to do it. It's always at reach. So when we think about this gesture controlled, of course we have to take some things into account. One of the things is that you have to end up with flexible gestures, in the sense that, of course, gesture has to be natural, as I said, but they have to be easy to learn. Okay, you can really think about different gestures like this, you know, something really complicated, because people will tend to forget. But also you have to deal with the variability, in the sense that each of us, if I tell you if you just to do like a gesture, put your finger on your lips, each of you will do it differently. I mean, somebody will do like this. So it's kind of this variability that you have to take into account when you train a system to understand this kind of gesture. Also the ambiguity. I mean, this is more of a social thing as well. I mean, for people, some gestures mean something, and for others don't. Okay, if I ask you, what gesture will you do to stop the playing of your TV? I mean, you will do many things, but of course, some of us will do different things. Okay. Also about this culture thing, you have to be very careful when you design these gesture control systems to do something that is not allowed in some cultures. I mean, I'm from Spain, from Barcelona, and if I go to a pub and order 2 beers, it doesn't really matter which side I use this, because I mean the bartender wouldn't mind if I do 2 beers like this. It's okay, but here I wouldn't do it here. So you have to be very careful. So you have to design a system which is flexible enough to deal with all these kinds of things. Also, I mean, you have to try to build robust systems. I mean, the detection that you need to do is usually, it will be done in some places that it will be difficult. I mean, think about a room full of people and you want to detect a specific gesture from a specific people. So of course you need to be robust and try not to perform, or not to detect gestures that are done accidentally. And finally, when you do this gesture, one of the main problems of these gestures-based interaction systems, it's to deal with the so-called, I don't know if you heard about this, the gorilla arm syndrome. It's has been said several years ago when these touch screens starting to appear. I mean, they were in tablets. At the beginning, they were thinking about screens that react to touch. And the problem with the gesture is that your arm gets tired very easily, so you feel like it's a gorilla arm. It's not part of you anymore. You're really tired, okay? So you have to try to do gestures which are fast, and they can be detected very quickly, so your arm doesn't get tired. Okay, so when you talk about the technical issues, so of course you are trying to build a system that can detect gestures robustly in a space and time. So you can see the entire image of the room, you know, what the TV sees. So you want to detect the gestures in a space. You want to know where it is located, so you can locate it to a specific user that has the control, but also on time. So every an hour watching a film, you have to wait for the gesture to appear. So that means that recognizing gestures, it's what in the community is called a highly unbalanced problem. I mean, there are very few positives, very few gestures that the TV should react on. And there are many, many times that the people will do something, will be talking, will be waving their hands, but you don't have to do anything. So it's a highly unbalanced problem that when you design the system, you have to use the tools that deal with this problem. And of course, I mean, there's other things that you should take into account. For instance, it should work in all illumination conditions. So you watch the TV without any lights on, it should work. Or if it's highly illuminated environment, like the demo that we were doing outside, it should also work. It is good if no background rendering is performed. You know, with this vision-based algorithm, sometimes what you need to do is that you need to know the background in order to be able to understand what people do, okay? So one of the nicest things that you can consider is try not to learn the background and work straight away in every place. And of course, if you're dealing with interaction, you need to do it in real time. So you cannot wait a couple of seconds, 3 seconds to understand the gestures. It has to be instantly. So what we have done then in the Fascinate project is create a module that would understand gestures with no device. And basically, it would understand 2 kinds of gestures. I will tell you a little bit more about. It will be some static gestures. What we call static gestures are gestures that are performed in a single moment. You don't need to move your hands like this shush thing. It's a static gesture. And some dynamic ones where you can navigate through the system. So you move your hand to navigate. That will be a dynamic one. Okay? So basically, what we will do is we will put a system, a gesture control system that sees the users that are watching the TV, and it will communicate with the rendering part. So it will tell it either to change the navigation, the panorama, what is looking, or lowering or augmenting the audio signal. Okay, so the functionalities that this gesture control system has are these ones. So the user will be able to navigate through the panorama. The users are able to switch between the satellite cameras, the regions of interest, and the panorama. They can play or pause and resume the video and audio accordingly. They can select the volume and also select the audio tracks. So if there are some commentators or different commentators in the track, the user will be able to change between them. And also the system supports multiple users, so there will be a way to take the control of the system. The same as we do at home with the remote control. No? The one who has the remote control is the one with the control of the interaction. And then, because there is no device, there will be a system or a way to change this. So the gestures that we thought will be interesting to use for the functionalities that I showed you before are this one. Okay, so people will be able to select it through the menus by pointing, and will be able to navigate by grabbing or by signaling the screen. So you move your hand, and your hand will be able to select anything on the menu, and then when you grab it or when you point it, you will be able to navigate. Okay? Maybe you have seen the demo outside, so you know a little bit what I'm talking about. So there will be a gesture to take the control, and also some gestures to control the volume. So you can do the shush, and the volume goes down. You can see here the feedback. You can touch your ear, so the volume goes up. You can cross your hands in front of your mouth, and the volume will mute completely. And finally, you can pause the video like this. As I tell you, this was kind of a gesture that it hasn't got a very natural way to do it. So how are we going to understand these gestures? Here's the architecture that we propose. So this is the architecture that we built in order to create a system that understands these gestures that I show you. Basically, the architecture is composed of 3 main layers. It's a vision-based solution, so we need a capture layer. I will tell you about the sensor that we're using to capture the information that we need. And then we will have an analysis layer, and we have 4 main blocks to do the analysis. So, of course, we are dealing with humans, so we need to locate the humans, and the way we are going to do this is by the head. So we will locate the head, and we will track it. And then after the head is located, we will use a hand tracking, so we will also locate the hands of the user. We will have a system to recognize these static gestures, so the shush and the ear. And finally, we'll have a system to recognize users. You haven't seen this in the demo because it's not already, but it's not put there because this is basically used in a home scenario. So you will have different users, and you will be able to give them different roles. Think about, for instance, the parents of the house will be able to do more things, more interactions than the children, for instance. So the system will recognize if it's the parent or if it's the children that it's there using the system. For that, I will tell you a little bit about this. Of course, you need to train the system about the users, and this demo with many people, we cannot do that, so that's why it wasn't implemented in this demo. Finally, we just need a control layer. So it receives the output of all these modules, and it will communicate with the render to pass the commands and to the Fascinate render system. So basically, if I go a little bit to each of these modules, to about the capture, what we are using to capture the information, the sensor we are using is the Kinect Sensor, the Microsoft Kinect. I'm pretty sure you've heard about it. This is a device, a sensor that Microsoft released, I think, 2 or 3 years ago, associated with the Xbox 360, the console that you play with. The good thing about this sensor is that as soon as it was released, I would say less than a week after it was released, there was already people tinkering with it and obtaining the raw data behind. And then after that, Microsoft also released an SDK, a software development kit, so you can play with it. You don't need an Xbox to play, just a computer. It's an USB device, plug it. And we say that you have 2 information from this device, which is a color image, a normal camera, it's here on the left, and a depth data here on the right. The depth data, the ones that you don't know, it's similar to an image, but instead of information about the color of each pixel, you've got information about the depth of that pixel. Okay, I mean here is just a false color, what we say. So the blue pixels means that it's
hands a lot. So anyway, I'll try to scream a little bit. Where was I? Well, yeah, the depth image has this information about the depth of each of these pixels. And the good thing about the depth image is that, well, two things is that, of course, it's independent of the illumination. So it will work with the light on or off. It will have information of this depth. It's also, this sensor has also information about the actual measurements of the depth. So you will know if it's 2 meters or 3 meters behind. So it's also useful. And basically, it solves a lot of the problems that this vision-based solution had previously, which is what we call the segmentation problem. If you think, of course, if you are trying to detect gestures, you are trying to detect hands or what the hands are doing, and so you have to isolate the hands from the rest of the image, right? So you want to segment this hand from the rest of the image, and sometimes doing that in color is very difficult. I mean, think about this image may be okay, but think about if I do with my hand, of course, my hand and my face are similarly in color, and so segment that is really, really difficult. I mean, some vision algorithm has been working on segmentation for a really long time, but then if you look at this depth data, segmenting the hand from here, it's very easy. I mean, it's just what is closer than 2 meters is the hand. So you can really segment, you can really do many things with this depth data. That's why recently most of the gesture-based systems that are appearing are using this depth data, either with this Kinect sensor or with other ones. The good thing about the Kinect sensor also, it is very, very inexpensive. I mean, for less than 100 euros you can get one. So it's very, very cheap. So anyway, that's what we are using. So you look at the demo when you go out. If you look on top of the TV, you will see the Kinect there, and that's what is connected to the computer. So if we move for a little bit, I'll talk you about the head tracking. So what we do to locate heads, basically we use an elliptical template, which is similar to the human head. So we resize the template based on the depth of the things appearing in the depth map. And we do a measurement of the similarly between the pixels and this elliptical template. And at the end, you do an score of these pixels, and you select the maximum, and that is where your head is located. So as you can see, this is a very simple approach. So it's very fast, so you can achieve real time easily. Here I put you some offline results. It's just to show you that using the depth, it's much more useful than using the depth data. So here what we try to do is we did 2 different experiments, trying to locate heads using the color only information, the image on the left that you saw from the Kinect, and in green is trying to do it the same, but with the depth data. So here you have some results. For instance, in this image, both of them are okay. But of course, when you include in the face, the color, which is the red one, is failing. So here you have the graph over time. This is time frames. So the red one now, it's using the depth map. The error, it's low. But of course, you use the color. Sometimes you get a very high error. So our system achieves more or less in this sequence an error less than 10 pixels, which are VGA resolution, which is 640 by 480. It's enough for our application. So here I can show you a video of it running. So what you see here is the depth map. So the darker you see is the closer to the screen. And what you see is that we locate the head. Quite nice. It moves with the people. And when another one comes, of course, if they put at different depths, so the algorithm works. So let's move to the other building block of this gesture-based interaction is the hand tracking. So as soon as you know where the hand is, you would like to know, where the head is, you would like to know where the hands are. So for that, what we propose is to have what we call a virtual box in front of you, it's a hand box. Okay, so once you locate the head, you say, okay, this is a virtual hand box. Here you can see it in green. This is virtual. It's printed overlay to the video. So as soon as you put your hands there, they will get detected. Okay, so you can detect 1 or 2 hands here in red and green. And how is it doing that? Well, we are doing that based on 3D points clusters. Here the idea is that you saw the depth map. You can convert the depth map into a 3D representation. Okay, so through a point cloud representation, what we do is each of the pixels, you put them in a point in a space. So there you can think that the hands will be like a cluster of points in the void of this handbox. Okay, so then we do some spatial and temporal coherence, so it's robust enough. But basically, that's it. And then to do the grabbing, so we have an algorithm to detect if the hand is open or closed, if you are pointing at it or open it. So the system can react differently. And here I show you some offline results as well. Here to try to see if the system was behaving correctly, what we do is we compare it with respect to the ground truth. So we did some videos with the Kinect, and we marked them manually, and we tried to see if the hands were detected correctly with our system. Here on the right, you can see doing the zoom, like this. And the straight line is the ground truth, and the points are the locations where the algorithm is saying that the hand is located. So it's more or less following it. And here, over time, you can see the error. And we found out that it has an error of about 3 and 4 centimeters, which for the size of the hand, again, it's enough for our application. And here you can see an online result. So you see that the head is tracking, and then we put this virtual box, and as soon as you put your hands in it, it's following them. You can see the box that it's moving because, of course, it's following the head, and the head is doing some small motion, so it moves. So we found out that was a problem. So as soon as you enter your hand, the hand box is fixed. So that's why it stops when you enter. But as you can see, I mean, the hands are detected, and we can build something on top of that. Here I show you a video of both things working together. So the head tracking and the hand tracking. The hand box here is just a square. In reality, it's 3D, just for the video. And you can see it's following correctly. Here you can see the delay. That's because we do a running average over time, so it tries to be robust. And of course, if you do an average over time, you tend to have a lag, and this is showing. This is the open hand and closed hand. Anyway. So we'll move into the Face ID. Just an overview of what we do. Sorry you cannot see this in the demo right now, but basically what we do to recognize faces is we use what is called a local binary pattern histogram. This is actually like you can think of this as a texture descriptor of an image, okay? The good thing about this local binary pattern is that it's illumination independent, and it's locally, so you can have different illuminations within the same image, and it will be independent to that. Of course, as I said to you, the head tracking, the hand tracking, both of them are using the depth image, but the face identification is using the color image, okay? So it hasn't got this ability of being illumination independent because it's based on the color image. So of course, if you want it to work in the many illuminations conditions, you need to use an algorithm which is like this one, which allows you to be illumination independent, okay? What we do basically is that we collect some models, okay? So before you stand up in front of the Kinect, it will record some images of your face. For each of the image, we do this local binary pattern histogram, and that will be saved as a vector, so that will create the model of that person. Okay, so a model is just a series of vectors, a series of histograms of these local binary patterns. So basically, when a new person comes in, you have the models already stored. When a new person comes in, it actually reduces to a classification problem. You can do the local binary pattern in the new person that appears. You don't know who he is, but you want to classify in one of the vectors, one of the models that you have. Okay. So for that, we use KNN. It's a simple way to do classification. KNN, it's K nearest neighbors. Basically, what it works very, very fast. If you use K equals 1, so you just find the first nearest neighbor of your test phase. Okay, so think about you have, for instance, two models, two persons. Person A is these squares. Person B are these circles. And then a new person comes in, so you don't know who he is this triangle. Okay, so you've done the local binary pattern, and the histogram is this triangle. So if you do one nearest neighbor, so you just find the nearest neighbor of this triangle. In this case, it will be this circle. So you will say, okay, this person is person B, and that's it. Okay. The problem with this one KNN is that you cannot have any confidence. So you do this, you just can say it's person B, but nothing else. If we go to a K equals 3, so you do 3 KNN, you can do something more. I mean, of course, you can do the same. You will look for the 3 nearest neighbors. In this case, so you have these 2 circles in this square. So you will say, okay, there are 2 circles, 1 square. It is person B, so you'll do the same decision, same classification. But of course, here you have some more information. Here you can say, well, because there are 2 circles on just 1 square, I'm pretty confident that it will be person B. It will be 3 squares, the 3 nearest neighbors. You will be much more confident. You will say, no, I'm pretty confident it's person B. So of course, using a different number of K allows you to give also a confident value. We also use a soft KNN, which means that you also take into account the distance of each of these neighbors. So of course, if the distance between the circles is much smaller than the distance to the square, so you have a greater confidence. So at the end, you have all this confidence for all these frames, because if it's a video, we try to do a temporal fusion of this confidence. So you average this confidence over time, and at the end, we do it every second, you do a classification. Okay? So sometimes, if the confidence is not very good and you are wrong in your classification, at the end you can solve it. And that's it about the face identification. I will talk a little bit about the last building block that we use, which is the gesture detection or gesture recognition. This one is used for the static gestures, the shush and the ear thing. And well, it's based on a technique presented by Shotton quite recently, 2011, and it's called random forest. Random forest using like a group of binary trees to do a classification. And we also use some boosted learning and an efficient process to be more robust. So like my colleague Jeff did before, I'm going to present or try to present you or explain to you random forest in 2 slides as well. But anyway, really quickly, as I said, random forest is a classification technique. So what we'll try to do is we will have a gesture or we'll have an image of a gesture, and we will try to classify it. Okay? And for that, we use a group of M decision trees, what is called decision trees. I will tell you in the second slide what a decision tree is made. But the idea is you have several decision trees. So when you got a patch, you got a region of this depth map, and you want to know what it is. So you run the decision through each of these trees, and each of these trees at the end will make one for you. I mean, it will say, okay, I'm thinking it's this gesture. No, I think I'm doing this shush gesture. No, this one will think that it's doing whatever, okay? But of course, the idea is that these decision trees, most of them will be giving the correct classification, and at the end, you average all the decision, and then you end up with a probability map. I mean, at the end, you just have a confidence that this gesture is, or this tree is saying that the patch is this gesture, and at the end, you average everything, so you have a probability that this patch is actually one of the gestures in your database. Okay? So how do you do these decision trees? Basically, it's a randomized process. So what you want to do is a binary decision. So what you want to do actually is to create a function that, with a threshold, decides which path you have to go in the tree. And you do that by getting the patch, a point in the middle. You get 2 random points. You measure the distance between the points, the distance in depth. So you know the depth of this point, the depth of this point, so you know the difference. And you basically create a threshold based on a training data. So you have patches of your gestures, and you train this equation so the threshold corresponds to a correct classification. So what you do then in the image is to locate the gesture. You go across the image. You select some patches, some regions of the image. You go through these all decision trees. So you go creating a probability map. You do that. I mean, I have put the color image, but you do that in the depth one. I mean, just remember that. So you classify all the patches, all the regions with this random forest, and at the end you got a confidence. So you average all this confidence over the image, and you end up with this. I mean, it's like a representation. So the red pixels will tell you that the random forest are confident that in that specific place a gesture is performed and is classified as this one. Okay. So in order to be robust, we do a spatial consistency and a temporal consistency. This temporal consistency, as you can think, is like it's a video, so we do a running average of this confidence over time. And the spatial one is just, okay, we'll just do an average of all the pixels around that are together. Okay, so you do an average on space and an average on time. So here are some offline evaluation. Basically, we compare with some similar algorithms in the state of the art, and in different manner. One it's class-specific, and the other one it's what we call multi-class. The difference is that in the class-specific, you train the random forest only to distinguish one gesture. Okay, so you have a random forest to distinguish only one gesture. The multi-class is that you teach your decision trees to distinguish between several gestures. Okay, of course. The multi-class have lower precision because it has to do more work. But in any case, I can show you an online demo which shows that more or less works. Here you can see the localization. So the localization is giving you this where these blocks are, and the color of the block is a different gesture. So you can detect all of them. And if you haven't seen the demo that it's outside, I encourage you to go and see it working. Okay, so basically I'm finishing now. I'll talk to you a little bit about this last layer, which is we call it the application control layer. And basically what it does is that it recovers all this classification from all the modules. So it will recover that a gesture is being done from the gesture recognition, that the hands are moving, that is this user, and it will make the decisions based on all that. Okay. It also controls the state of the interface. And one thing that is very important, it will provide feedback to the user. From the studies that a colleague of us in the project TII has performed, we found out that if you want to build an interaction system, it is very important that you give feedback to the user. So user knows if the system is responding, if it's not. If you want it to, with gestures, navigate through the screen, it has to know where the hand is to move it. So it's important to, somehow we decided to do an overlay on the screen, give feedback to the system, or to the user, sorry, that the system is understanding the user. And finally, as I said, it communicates with the rendering, and for that you use an XML protocol. XML, it's text-based protocol. At least the information that we need to send is not much. So basic XML protocol works okay. So for the future work, I mean, as I said, we've done some usability studies for this Fascinate project. We found out the importance of feedback, for sure, and also that maybe the navigation paradigm that we're using might not be very correct, so we might change it. Right now, as you said, use your hand to pan and zoom, and somehow it's hard for the user to do that, so we might change it. We find out that the gesture part, the static gestures, were okay. I mean, people were actually acceptable of this kind of user and thought they were natural and good. And also one of the things that we are trying to do as future work is a dual setup. We're trying to set up not one Kinect but two Kinects, so one closer to you, so you will be able to do something with your fingers. I mean, we have to think a little bit about this, but the idea is to avoid this gorilla arm syndrome by using your fingers to do the gestures will be more easy to do. So we hope that it will be more usable. And that's it. Thank you for hearing me. And if you have any questions, I'm happy to try to answer them.